Hi everyone, welcome back. This is Earth and Space Science 101. We're still on the unit on water on Earth, and this lecture is actually going to be on petroleum. There are some similarities between dealing with oil and gas in the subsurface and dealing with water in the subsurface. So that's why I decided to put this as part of the water unit, not in something like maybe the rock and mineral unit. It tends to make a little bit more sense here. So this is going to be lecture 16, and the next couple of lectures we're going to continue to talk about water on Earth. We're going to talk about groundwater, and then we're going to finish out this unit talking about glaciers. So let's get into petroleum in general, mainly oil specifically in this lecture today. And we'll start with defining what petroleum is in the broader context. Petroleum resources are going to be linked in with oil and gas. They're going to exist as fluids if we're talking about crude oil, and natural gas is going to exist obviously as a gas in the subsurface. So if you're going to deal with a fluid or a gas existing in the subsurface, there has to be room for that fluid or gas to exist, and there needs to be the ability for that material to move around in the subsurface. So when we're talking about rocks or loose unconsolidated sediment that has the capacity to store and transfer oil and gas, we talk about stuff that has high porosity and high permeability. So before we even deal any more with oil and natural gas, we're going to spend a little bit of time talking about those two terms. We're going to define porosity and permeability, and we're going to look at some different rocks that have a high porosity and high permeability. These are going to be rocks that are not only good reservoir rocks for oil and gas, these are also going to be rocks that are good aquifers. That's going to be a water-bearing rock. That's going to be something that we're going to talk about in the next couple of lectures. So this topic kind of transfers through to the next few lectures. Porosity is just the sheer percentage of available space in sediment or rock to store any kind of fluid, whether it's water or oil, or even if it's a gas, in the case of natural gas. So it's just a basic measurement of the ability of that material to store fluid. Typically, sediment is going to have a higher porosity than most rocks, and sedimentary rocks are the ones that have the most available pore space, and so the highest porosity. So in this picture, you see this glass jar full of marbles, and there's a tremendous amount of space in between all of those marbles. You can completely pack that jar full of marbles, and there's still plenty of space available. So you could fill up that jar with water, or you could fill it up with oil. And the place where that oil or that water would exist would be the available pore space. So not only is that jar of marbles porous, it has a high porosity, it also has a high permeability. So there's an interconnectedness of that pore space. So it makes it easy for a fluid like water or oil to move through those marbles. If we're dealing with something that is going to actually be a naturally occurring substance, if we're talking about sediment or sedimentary rocks, then the materials that tend to make good reservoir rocks and good aquifers and have the high porosity are going to be your sort of medium to coarse grain clastic sedimentary rocks, and typically things like fractured limestones. So something like unconsolidated sand is going to have a pretty high pore space, anywhere from 25 to 50% depending on the grain size of the sand. Gravel, if you don't have any other sand or mud, would even have an even higher pore space. Something like a sandstone, so that would be an actual lithified rock as opposed to loose unconsolidated sand, that would have a lower amount of pore space, but still something that we would still could consider porous. It would have something like 20 to 30% porosity. If we're talking about something that doesn't have a lot of porosity at all, you're thinking of more like the fine-grained clastic sedimentary rocks, or the unfractured limestones, or most igneous or metamorphic rocks. Those tend to have much, much lower amounts of pore space, sometimes no pore space at all. So something like shale would be a good example of a fine-grained clastic sedimentary rock. It has somewhere between 0 and 10% porosity, depending on the amount of fracturing in the rock, depending on the amount of maybe larger particles. All that kind of stuff would possibly increase that porosity a little bit. So the next term that goes hand in hand with porosity, it's also important, is that term permeability. To have something that is permeable means that you can have a fluid or a gas move through it. It's permeable to that particular material. And all that means is an interconnectedness of the pore space. So for something to be permeable, it inherently also has to be porous. You can't have something that's permeable without also being porous, because it's an interconnectedness of that space, that pore space. So things that are typically permeable are going to be things like sandstones, limestones, coarse-grained clastic sedimentary rocks like conglomerates and breccias, and things like shales and crystalline rocks like granite, basalt, all of your different metamorphic rocks like quartzite, anything that you would really build maybe like a countertop out of. Those are going to be rocks that are not going to be very permeable. They're going to be impermeable. Now, if we wanted to get into this a little bit more, there are mathematical terms that you could use to show exactly how much permeability a rock might contain. And those are usually framed around the idea of how much force is required to move a fluid through the rock. But for us, we could just use simply the idea that something is either permeable or impermeable. Either something is high permeability or low permeability. And it's really important to remember that things that are permeable to one fluid, like oil or natural gas, those are also going to be permeable to water as well. So this is important for not just the lecture today on oil and gas. It's also important for future lectures when we deal with groundwater as well. So coarse to medium-grained clastic sedimentary rocks, sandstones, conglomerates, breccias, unconsolidated sediment, so just sand, gravel, that kind of stuff, and fractured limestones. Those are all going to be great reservoirs in terms of oil and natural gas, and great aquifers, because in both senses you can store and transfer fluid. These are rocks that are going to have high porosity and high permeability. So that's going to kind of tie in today's lecture with future lectures on groundwater, and all that stuff about porosity and permeability continues to be important to future lectures. So from here on out, today we're going to talk specifically about petroleum resources, mainly oil and a little bit of natural gas as well. So oil and natural gas is derived from organic material. It means it's derived from something that was at some point alive. That's why these are referred to as fossil fuels. Now, typically we think of fossils as large organisms, things that leave behind big imprints. So you think of a brontosaurus in your gas tank when you're thinking about where the gasoline that fuels your car actually came from. But that's not completely correct, because most of the stuff that's really going to form oil and natural gas is going to be microscopic organisms. This is going to be stuff like algae that at some point lived on top of the water column in the ocean. When it dies, it falls down to the bottom of the water column. It is going to be put in place with all of these finer grained clastic sediment, so all this stuff like clay and mud. And then over time, it gets deeply buried. And it's the burial that converts that organic material into oil and natural gas. So let's look at this sort of one step at a time. Let's look at this from that first step of the type of sediment that's going to be buried along with all of that organic material as it gets to the bottom of the seafloor. So take, for instance, right now out in the Gulf of Mexico, you have all of this life, all this microscopic life that's on top of the water column. It lives out its life as maybe blue-green algae, maybe red algae, and other kind of planktonic organisms. And all of that stuff eventually has to die. And when it does, all that stuff, all of those little bodies, all those little microscopic organisms are going to fall down to the bottom of the ocean, and they're going to be deposited on the floor of the ocean. Now, it's the type of sediment that's buried along with that is going to allow it to eventually get deeply buried and be eventually converted into oil and gas. So that's the first step, the first sort of big buzzword in the formation and trapping of oil underground. For oil to form, it has to be buried along with something called a source rock. So it's not necessarily that it really has to be buried with this fine-grained material. It just happens that in the kind of environments where you have all of this slow deposition of sediment occurring, that's going to be where fine-grained sediment is going to get deposited, and not necessarily where your coarse-grained sediment gets deposited. So if you remember from previous lectures on rivers, you get coarse-grained sediment like sand being deposited at the mouth of rivers. Farther out into the ocean, where you have all of these organic creatures living and dying and being deposited on the seafloor, that's where all the fine-grained sediment is going to be deposited. So it's first deposited on the seafloor and then buried over time as part of the source rock. And it's called this because this is the source of all of this stuff that's going to turn into oil. It's where the oil is going to originally form. Now, the source rock has to be deeply buried. That's a really, really important part of all of this. And that's the part of the formation of oil and natural gas that takes a tremendous amount of time. To take all of that mud and organic material and little planktonic organisms, all that algae and stuff, and bury it thousands of feet underground is going to take a really long time, at least hundreds of thousands, if not millions of years, for all of that material to be buried to 2 or 3 or 4,000 feet underground. So it's when all this material is buried, thousands and thousands of feet underground, that it begins to be converted to oil. So if we think about what these creatures look like when they were buried along with that mud and that clay, they have a structure at the atomic level where the bonds between the carbon and the hydrogen and the oxygen are going to make fairly complex molecules. You know, you're going to have lots and lots of carbon atoms and lots of hydrogen, lots of oxygen. But once that material gets buried, and that stuff begins to convert to oil, the reason why it's converting to oil is because the hydrocarbon bonds are being broken down into smaller and smaller and smaller bonds. And so that's called hydrocarbon cracking, taking all of those complex molecules and making something fairly simple out of it. So in order for that to happen, in order to crack the hydrocarbons, you need an increase in temperature and pressure that you find with depth. As it turns out, that depth is around 2 to 4 kilometers below the Earth's surface, and the temperatures and pressures that's associated with is around 60 to 120 degrees Celsius. So that puts you sort of in a broad range around the boiling point of water, certainly a lot higher than Earth's surface temperatures, where 25 degrees Celsius is sort of your standard temperature. And then you have the pressure that goes along with that. We have 1 atmosphere of pressure at the Earth's surface, and at depth, you would have maybe 2 to 3 atmospheres of pressure. So 2 to 3 times the amount of pressure that we experience on the Earth's surface. So at those temperatures and pressures, which naturally occurring you only get with depth, you're going to convert all of that material to oil. That's called the oil window. If you don't get to the oil window, if you're a little too shallow in your depth, and you don't have those temperatures and pressures where that oil is going to form in peak conditions, you form a fairly useless substance called kerogen. It's sort of like a precursor to oil, because once that material is buried a little bit more deeply, which it eventually will be buried a little bit more deeply, then that material would further crack and convert to oil. If you go past the oil window, if your temperatures and pressures are too high, then you don't form crude oil anymore. You form natural gas. It's mainly going to be methane that's going to form at the kind of temperatures and pressures that you see past the oil window. So it's right at that oil window, not too hot, not too cold, right in that window where you have the temperatures and pressures where you're converting that material mainly to oil. And now this oil isn't immediately going to be able to be used in your gas tanks in your cars and for energy. It needs to be refined at the surface so you can extract out and further crack out the hydrocarbons down to get maybe a larger amount of just pure octane if you're trying to convert it to gasoline. So depending on what it is that you're trying to extract from this, you have to refine it further. But at least we now have the source of what most of the Industrial Revolution, still most of where most of our energy is coming from. We have the oil. Now, okay, if we put it in the context of the broad picture here, we had the source rock first, that deeply buried source rock that's fine-grained, rich in all that organic material. It's buried deep enough to get it into the oil window, and now you've turned all that material into oil. To paint you a little picture of what the area around all of this oil looks like, you're mainly going to have a lot of water in that pore space. Water is going to be buried along with everything else, along with all that organic material, along with all that sediment. At depth, you're going to have mainly really salty water. You're going to have basinal brines. So you're going to have brines that are, you're going to have groundwater essentially that's maybe 4 to 5 times the salinity of seawater. So once that oil forms, it's immediately going to want to rise because it's in contact with water. And we know what happens when you mix oil and water. They separate. Oil rises because it's less dense, and the water stays at depth, especially if you're dealing with a dense water like a salt water. So the separation between those is pretty immediate, and that oil is going to want to move. So that's where the next step in this whole operation comes from. The oil is going to move from the source rock, where it has a low porosity, low permeability. It's going to be essentially sort of squeezed out of that source rock, like squeezing water out of a sponge. And then it tends to move into areas where it has more room to flow around. It tends to move into sediment that is going to be larger in grain size with more space in between the grains. It tends to move into things that we call reservoir rocks. So this is the same place again where you see a lot of water with depth. So it's going to continue to move once it gets into the reservoir rock. But once it starts this process of moving, it's going to move out of the source rock and into reservoir rocks, various reservoir rocks at depth. So the important thing to remember here is that if the oil is actually in this process where it's moving, it's always going to want to move upwards because it's less dense than the water. So it always wants to move towards the surface. And secondarily, it's always going to want to move from something that has low porosity and permeability to something that has high porosity and permeability. So it always tends to want to flow out into the reservoir rock. It's kind of like you maybe escaping a really crowded room out to some place where you have a little bit more space to walk around, a little bit more space for your elbows to move around. It's the same thing that this oil is doing. It's moving out to something where it has more space to flow. Now, that reservoir rock may potentially extend all the way up to the surface. So then that oil can flow through the reservoir rock and continue to flow all the way up to the Earth's surface where it leaks out onto the seafloor. So at that point, it's fairly useless for us as an energy resource if it's moving up to the surface all on its own and escaping all on its own. It doesn't have a chance to pool up underground in any sort of economically feasible pool of oil to extract from the subsurface. So the last thing that's important in the process of creating and trapping oil underground is some set of natural conditions that keep the oil in place instead of allowing it to flow all the way up to the surface. And reservoir geologists are pretty, straightforward, simple people. They call this an oil trap. It's the set of conditions that keep oil trapped underground. It's pretty straightforward. Now, these set of conditions can be anything but straightforward, but they range from structural conditions, so things like folds and faults that take porous and not very porous material and align it in a particular way that keeps that oil trapped underground, or it might be something a little bit more of like a stratigraphic set of conditions. So something involving the sediment that's being buried, trapping that oil underground. So whatever the set of conditions, it basically just has to allow for oil in the reservoir rock to stay at depth instead of allowing it to move all the way up to the surface. So let's look at maybe one of the most simple conditions that would allow this to take place and go kind of run through a little bit of a hypothetical scenario here. In this little cartoon picture, and it's out of your textbook, you have essentially what's sandstone in the lower half of this picture. Everything that's pictured with that sort of polka dot pattern with all of the little stipple patterns on the picture, that's all supposed to represent sandstone. So you know you have a whole lot of reservoir rock, you have a whole lot of sandstone at depth. Closer up to the surface, you have a layer of shale, and that layer has been folded. So instead of being laid out flat, horizontal with respect to the Earth's surface, it's been folded. So there are these upwards facing folds and these downwards facing folds. So what happens here is once that oil forms, it's rising up through the water, it's moving up towards the surface, and then it tends to pool in one of these upwards facing folds. In structural geology, we call that an anticline. It tends to make an A, right? You know, you have all of these folds sort of pointing upwards. So all that oil then wants to move up into the anticline where it ends up trapped because it can't flow through the shale. So that layer of shale ends up acting kind of like your roof trapping heat in your attic. That heat can't then rise up past the roof, so it just stays there. In the subsurface, all that oil's moving up towards the surface, and it gets trapped by that almost sort of roof-like structure of the shale. Then it pools up in this large reservoir, and then it becomes economically feasible to drill a well. And sometimes these could be multi-million-dollar wells, so it's a pretty big proposition for somebody to undertake drilling one of these. Drill it into that resource, and then extract it. We have ways of being able to actually look at the subsurface without drilling wells to tell whether or not the conditions are right for oil to be there and to be able to even image the oil. It all has to do with seismic waves. We can use seismic reflection to identify where the oil exists and where the types of rocks that store that oil are going to exist in the subsurface. So then it becomes less of a risky proposition to drill that well under the risk that it might be a dry well. So that's just one potential oil trap, the anticline trap. And that's a pretty simple overall trap. You could have something similar exist if you have faulted rocks, where the numerous faults and the impermeable rocks act again as sort of a roof that's keeping that oil from flowing up to the surface. But that's not what we have the most of in the Gulf of Mexico. In the Gulf of Mexico, we have a thriving oil and gas industry, mainly because of the existence of these things called salt domes. So to understand why salt domes are the most important, the primary oil trap in the Gulf of Mexico, you kind of have to get into a little bit of the history of the Gulf of Mexico. This is going to be relevant not only to this lecture, but future lectures on groundwater in South Louisiana as well, because these salt domes can sometimes compromise the quality of our groundwater by introducing salt into freshwater aquifers. So first, before we get into the way that the salt domes are acting as an oil trap, let's look at the history. So when we get into the history of South Louisiana, you really have to go back hundreds of millions of years ago. The first picture that I'm going to show you that gives you kind of a set of conditions that are going to lead the way to all this salt forming in the Gulf of Mexico starts back 180 million years ago. These images that I'm going to use for the next few slides showing you the history of the geologic history of South Louisiana were drawn by my former advisor over at LSU, Dr. Jeff Hainer. So what we have 180 million years ago is the very beginning of the breakup of Pangaea. So you remember all of these continental land masses were all aligned together as one big supercontinent, and they continued to break apart after that. So first, North America and South America separated from Europe and Africa, creating the Atlantic Ocean. That's the part we probably remember. But also, North America and South America started to separate. And there was really another sort of mid-ocean ridge, another spreading center or divergent plate boundary that was doing that work, separating North and South America. So they continue to separate, and then we're going to flash forward in time to 160 million years ago. So we're going 20 million years into the future from that first picture. Now we have a picture of sort of what the Gulf of Mexico looks like now with some notable differences. The Gulf of Mexico at this point was a little bit smaller, and most importantly, it was cut off from circulation with the rest of the oceans of the world. It was a landlocked interior sea, completely saturated in seawater. So 160 million years ago put you in the Jurassic period. So some of the dinosaurs from Jurassic Park are really just starting to evolve on the continents at this time. And out in the Gulf of Mexico, you have this big landlocked sea, sort of the Gulf of Mexico that was. Temperatures were also way higher at this time. So both because temperatures were higher and because this was a landlocked feature, the water in the ocean started to evaporate out. And it did so to the point where the water was actually supersaturated with respect to halite or salt, table salt. So tremendous amounts of salt, miles of thickness of salt was deposited on the floor of the Gulf of Mexico 160 million years ago. Some of that would have later been sort of dissolved away, but we still have enormously thick deposits of salt underneath all of the sediment on the Gulf of Mexico. And this layer of salt is called the Luan salt, and stemming from Louisiana. So first you deposit all this salt on the floor of the ocean. Then later on, over millions of years, over the next 100 million years or so, rivers like the Mississippi River began to deposit sediment on top of that salt. So salt and stuff like sand and clay have the same sort of relationship between water and oil. Oil is less dense than water, so oil wants to rise through water. Salt is less dense than stuff like sand and clay, so it wants to rise up through that sand and clay. Even though it's a solid, it still has this ability to move up towards the surface just like oil does. It just takes a lot longer. So this salt actually moves up towards the surface because it's lower in density, and it forms these things called salt domes. These are not small features at all. These are features that are maybe 5 or 6 times the height of the Empire State Building and as big around as, maybe the entire city of Baton Rouge. These are huge pillars of salt in the subsurface that are extending upwards and moving upwards. As they move upwards, they do 2 things. They will occasionally dissolve into freshwater aquifers, especially up at the top where the water is going to be the most fresh, and that's going to impact groundwater salinity. That's going to be something we're going to talk about in the next lecture. And they take all of these originally flat layers of sediment around them and they warp them upwards around the salt dome. So this is what you ultimately end up with. You have a salt dome. And in this picture, you're seeing the salt represented with the rock salt with this sort of plus pattern. All these little crosses are representing where the salt is in the subsurface. And then the dashed pattern and then the stipple pattern, the polka dot pattern, are representing the sediment surrounding it, the shale and the sandstone. So because those layers are warped upwards around the salt dome, the oil that's flowing up towards the surface gets trapped up against the salt. So the salt is crystalline, so the oil can't flow through the salt, and it can't flow through the shale, the impermeable rock. So it moves upwards through that sandstone, the only rock that it can actually move through, the only one that's permeable and porous, and then it gets trapped up against these salt domes. So the really interesting thing about looking at the entire Gulf of Mexico and looking at where oil platforms exist, not only offshore in the Gulf of Mexico, but onshore as well, is that all of these oil platforms and all of these oil derelicts are all positioned around these salt domes. So if you know where the oil platforms are, you in a sense know where the salt domes are. And the oil industry knows this. They know that these salt domes are excellent traps for oil and gas, and so they can extract large quantities of the oil and gas from around those salt domes. So the Gulf of Mexico is just one of the really important oil fields in North America. We have oil essentially anywhere where you have a large basin at some point in the past that at some point was full of water, where all of those organisms could fall down to the bottom of the seafloor and die and become buried over time, and you have the right conditions in place to trap that oil underground. So that's really sort of all over North America, but most notably through the western part of North America, where the big Cretaceous interior seaway was around 100 million years ago. That was a seaway that actually connected the Gulf of Mexico all the way up to the Arctic. So all throughout there, you have large oil deposits. You have them on the north slope of Alaska, and probably the largest oil field in North America is probably in the Gulf Coast area. And that's obviously the one that's most important to our economy here in South Louisiana. Now, as we continue to use oil, as we continue to use it at an alarming pace, the easy-to-extract oil pools underground have really, in a large sense, been taken already. It's sort of a matter of anything that's going to be easy to access and economically cheap to access is going to be really the first to be recovered from the subsurface. What remains are the smaller pools of oil and the ones that are the more difficult to extract from the subsurface. So it's really taken the oil industry having to get really smart about how they extract oil and gas and how to do it the most efficiently, how to do it the most cheaply, and how to use other techniques to try to get as much oil out of the subsurface as they possibly can. One of these techniques has a large set of associated problems, and you probably have heard of it as fracking. Fracking is sort of a short name for hydraulic fracturing. It's the process of taking water and pushing it into the subsurface at a very, very fast rate in order to take really the source rock of oil and break it and fracture it. And once you fracture that rock, you've increased the porosity and permeability, and you allow that oil to be more easily extracted from that resource. So it takes injection wells, and it takes a main well that's actually taking most of the oil and pulling it out of the subsurface in order to do this most effectively. So this opens up a whole bunch of places where a lot of oil and natural gas exists that has, at least in the past, been untapped because it's hard to get this oil to actually move through the source rock. So if you're drilling a well just into the source rock without doing this fracturing, you tap into oil, but you're trying to pull it out of the subsurface when it doesn't want to flow through the subsurface. So it's too slow to be economically feasible to run these platforms without fracturing. Now, the problem with all of this fracturing is that if it's done really sort of in the wrong way, if it's done without a really good understanding of the geology of the area and the hazards of things like contaminating the groundwater system and introducing earthquakes into an area, it can lead to more problems than it's really worth. So it's something that really needs to be very, very highly regulated to be done safely. So the last thing that we're going to do is go on a little field trip that's going to show you, some of the things that we've talked about today and show you an actual oil platform, one that's out in the Gulf of Mexico. So I hope you enjoy this field trip, and that'll kind of wrap it up for today. As promised, we're going to go look at an actual oil platform. This platform is today no longer in existence because this is, of course, the BP Deepwater Horizon platform that famously led to the largest oil spill or largest environmental disaster in history, in world history, in the summer of 2010. So this was a platform that was located directly southwest of New Orleans. So this is an offshore platform. Through the course of this summer of 2010, between April and September of 2010, 4.9 million barrels of oil were spilled into the Gulf. It took those entire 5 months to seal this well, and BP ended up paying $65 billion between all of their charges and penalties, and most notably the cleanup cost. This is a disaster that we certainly don't want to repeat into the future, which is why after this spill took place, many regulations on safety were put in place so that something on this caliber will hopefully never happen again. Until next time, keep rocking.